So let's start with the basic concept of support vector machines. We know by now that support vector machines are supervised machine learning method, which means that we give it training data samples with every data point belongs to either one of two categories. Then it builds up a model that takes a new data sample and then assign it to one of the two categories we talked about. So let's start with the basic one-dimensional data, right? Let's say that we have the height of a bunch of people. Oh, let me just get a black color. So let's say this is the height of people in centimeters, right? So we tested the height of like a bunch of people to know if they are tall or not. So let's say we have okay, we need a circle, not. So let's say we have one here, one here, one here, one here, and one here, right? And then we have a bunch of people here, oops, here, 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 here. So we have two categories, like the red represents that they are not tall, and the green ones represent that they are tall. So now we need to pick a threshold. So let's say like something like this, because if a new data come to that model, we need to categorize it as either not tall or tall. So let's say we pick a threshold randomly by saying like this one. Is this the optimal threshold? Let's test it. Let's say we have a new data point that indicates to this point, right? By this threshold, we the model will tell us that this point is tall. But is it true? But it doesn't make sense because this point is closer to not tall rather than tall. So this is not the optimal threshold. So the basic idea of SVMs is we need to maximize the distance between the closest point to the threshold, like this one and this one. We need to maximize the distance, which means that we need to pick the threshold like this. Right, so this distance is maximized and this distance is maximized, and that distance is called margin. My handwriting in the mouse is not that good, but this distance between the threshold and the closest data point in each side, it's called the margin, or the street. We will talk about why it's called the street in another example. So we need to maximize this. We need to maximize this margin. So like when we have the same example here, when we have the data points here, this will classify as not tall, and that will be a correct classification because it's closer to the not tall example. Let's have another example that are two-dimensional. Let's say we have the height now, and we have the weight, and we have like these people. Let's say we have a height and weight to determine if they are obese or not. So let's say we have a bunch of data points here, 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 here. Just for I'm writing this. This is not accurate, but just for the sake of the explanation. And we have another data points here, 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 here. Okay, so the threshold will be picked the threshold which is the maximize the distance between these two and this one. So this is the most important ones. This, and this. So the threshold will be something like this, right? With the maximum distance between these and these. Let's print it more accurate. Okay, this is why it's called the street, because it looks like a street. Like this distance is the margin, and this is the margin. But in in SVM terminology, this is called the decision boundary. This dotted line, which is the dotted line in the street, and then it's the margin, and if it's the decision boundary if the data is more than 2-dimensional. Let's say it's 3-dimensional like this, or 4-dimensional. I don't know how to draw 4-dimensional, but it's 4-dimensional. It's called the hyperplane. You can refer to this one as a decision boundary or a hyperplane, but it's usually talked about as a hyperplane in higher dimensions. So that's the basic examples of what we talked about before in support vector machines. So now just go through the model, and in the next video we will talk about more about support vectors and the math behind all of this.